In grad school, one of my favorite classes was algebraic topology. This unique field of mathematics breaks down complex geometric objects into their most fundamental properties and bridges the gap between geometry and algebra by relating these basic components into algebraic groups. Algebraic topology led to the Banach-Tarski paradox, which is one of the most controversial results in all of mathematics. Today, I want to share with you one of my favorite proofs from this class, proving Brouwer's fixed-point theorem. And don't worry if you're not a graduate student in math. You don't have to be. This proof is beautiful in its simplicity, and I'll go over all of the key concepts in a simple and understandable way. But first, we need to talk about some of the fundamental ideas. Let's introduce the most important concept in the field, the fundamental group. The fundamental group is denoted by pi1 of x, where x is a point set. And without getting into the nitty-gritty detail, it essentially reduces objects to their most basic forms. A disk, for example, is equivalent to a point, because you can shrink the disk continuously to a point without breaking its structure. In this case, the fundamental group is the identity. A shape like this one, on the other hand, can be continuously transformed into a circle, but we can't shrink it further without removing the hole in the middle. In this case, since we can loop around the circle infinitely in either direction, the fundamental group is the integers under addition. The only other concept we need to know is that two structures with different fundamental groups can't be mapped continuously onto each other. Now, let's look at the theorem and the simple proof using these powerful tools. Brouwer's fixed-point theorem says, every continuous map from a disk onto itself has a fixed point. So f of x equals x for some x in D. Well, suppose this wasn't the case. Then we can construct the map R from D into S, where for each point x in D, we map the ray from x to f of x to the point where it intersects the boundary circle S. This map is continuous and therefore maps D into S, but that contradicts our knowledge that D and S have different fundamental groups, and therefore we find a contradiction and our proof is complete.